4.2 Linear Approximations and Differentials. We've used derivatives to compare related quantities that change over time. Now we're going to use derivatives to approximate functions locally using tangent lines. On the screen you see a blue curve that's graphed. So this is a function. And we're going to say that this function is differentiable at a point like x equals a. I'm picking to use a as 1. And so I've plotted a point that corresponds to x equals 1. And at this point, I've calculated the tangent line, which you see as the red line graphed. So using the known point at x equals a, we've created a tangent line, and we're going to use values on this tangent line to approximate the values on the blue line. Now, when we say that we're going to approximate a function locally, let me show you what that means. If I were to pick a point like 2, x equals 2, the tangent line approximation is here, I've circled it in red. The actual function value is on the blue curve. I've got that circled in blue. So we've got the actual value, and we have the approximate value. So we're going to use the tangent line value as if it were the actual value. So we're going to use that as an approximation. Now, because we're far away from the known value at x equals a, these 2 points are pretty far apart from each other. But if we were to come closer to that gold point, we would see that the actual and approximate, they're much closer to each other. And if we were to go even closer to the gold point, the actual and approximate are very similar. And so we can use this idea that a tangent line will give us a good approximation of the actual function value, so long as we stay in a local area. Now, this idea of what is close enough, it's going to depend on each and every function we look at. In this case, going from x equals 1 all the way up to x equals 2, that started to break down our approximation. It was not very good. But if we stayed at about 1 to 1 1/4, we can see that the actual and approximate values are very similar. Not all functions will have that same range, so we'll have to look and check on each one. What's a decent distance to call local? Let's take a look at how this works using a tangent line to approximate a function value. Here we're looking at the function f of x equals square root x. And we're going to use the anchoring point at x equals 9. This is a good point to use because at 9, we are able to find the exact value of our function. So at x equals 9, f of x becomes square root of 9, which is 3, which is a nice clean number. But the real number we want to calculate is what happens to our function when we plug 9.1 into it. Well, this is not one that we can work out with pencil and paper. We'd need a calculator to do it. Or we can do linear approximation. Linear approximation involves finding the tangent line. So that's the first thing that we're going to do, is calculate the tangent line. In order to do the tangent line, we know we need the derivative. So let's find the derivative of f. We're going to take the derivative of the square root of x, which I'm going to write as x to the power of 1/2, so that we can use our power rule to say that derivative comes out to be 1/2 times x to the negative 1/2, which if we wanted to, we could write it like this. And since we're calculating the tangent line at x equals 9, we're going to plug that into our derivative. So this is the slope of our tangent line at x equals 9. Now from here, we're going to put together the things that we know to create our linear function. We're going to call that capital L of x, and that's going to involve our function at the known point that we're using, plus the derivative at that same known point times the change in x. Oh, didn't mean to write x1 there, that should be an a. In this case, the a value is the known point, so this x equals 9, this is what we're using as a. So our linear function will look like f at 9 plus the derivative of f at 9 times x minus 9. And we can replace the pieces that we know. F at 9 came out to be 3. The derivative at 9 came out to be 1 over 6. And this function is our linear approximation function. This function will calculate an approximate value using the tangent line. So if we wanted to find the approximate value at 9.1, we're going to plug that into our linear function. And then we'll evaluate and simplify. Plugging this into our calculator, I'm getting 3.016 repeating. So using our linear function, we're able to approximate that f at 9.1 is approximately the same thing as L at 9.1, which was 3.016 repeating. If we wanted to, we could compare this to the calculator's answer for square root of 9.1 and see how different it really is. So if we did f at 9.1 without the linear function, that would look like the square root of 9.1. And if we type that in, we get 3.016620626, and this could be rounded. My calculator stops right here, so who knows what continues after that last 6. But if we compare our answers, the approximate value from the linear function is very close to the value that we get from our calculator using the actual function. And so this is the idea of this section for linear approximation, that if we stay very close to the point that we know the true value for, we can use a tangent line to approximate values around that point on our function. And if we wanted to look at this graphically, we could see the two graphs that I've got plotted. So the blue curve, that's the original function, square root of x, and we are plugging in the value 9. So we're looking around the point x equals 9. So we've got the gold point plotted there on the actual blue line. And I also have the red point plotted on the tangent line at about 9.1. So this red dot is the point on the tangent line. In other words, the L of x function. So this is the point that we plugged in 9.1 into the L of x function. And because this is zoomed out so much, the graph on the left, those points look like they're perfectly on top of each other. If we zoom in, we can see the graph on the right. And when we compare the values from the actual point that we know at 9, so this is our anchor point, we are approximating a little bit away from that at 9.1. And we can see that the red dot is on top of the red line, and we can see the true function, the blue, is right behind it. So these points are so close together that they're almost right on top of each other. They're only off by a very minor decimal. Let's look at another example here. This time the function we're looking at is sine x. We're anchoring at x equals pi over 3, and we want to approximate the function value at 62 degrees. Now notice that x equals pi over 3, this is the radian equivalent to a 60-degree angle. So 62 degrees is very close to 60 degrees. So we're going to create our L of x function using the known value of f at pi over 3 plus the derivative of f at pi over 3. And then we're going to multiply that by x minus pi over 3, just like we did in the last case. So we need to calculate a few things. Let's find f at pi over 3. That's going to look like sine of pi over 3. And we can use our memory for this one, if you remember your trig calculations, or you can pop it into your calculator. Find that sine at pi over 3 is equal to root 3 over 2. Now we also need our derivative at pi over 3, so let's first find our derivative. The derivative of sine x is cosine x, so then we're going to plug in pi over 3 to that derivative, which is cosine at pi over 3. Again, do this by memory or plug that into your calculator. And we find 1/2. So to finish off our L of x function, we have root 3 over 2 plus our derivative at that pi over 3, which is 1/2, times the change in x, x minus pi over 3. And this is our linear approximation function. And we're going to use that to evaluate the linear function at 62 degrees. So we'll have root 3 over 2 plus 1/2 times x minus, whoops, not x, we're plugging in 62 degrees for x. And I had pi over 3, but I'm going to write this in the degree measurement since we have radians and degrees. I'd like to keep them all the same. So 62 degrees minus the degree equivalent of pi over 3, which is 60 degrees. And we're going to clean this up and calculate. So we've got root 3 over 2 plus 1/2 times 2 degrees, which would just come out to be 1. And type that into your calculator. And we can get an approximate value of 1.866025404. That's as far as my calculator goes. So this linear function says that at about 62 degrees, this is what you should expect using our tangent line. Now if we compare that to the actual value at 62 degrees, so we're looking at what is the true value sine at 62 degrees. We can use our calculator for this. Remember though, you need to be in degrees if you're going to type this in as degrees. So sine at 62 comes out to be 0.882947593. Now, last time when we did our linear approximation, these numbers were very close. These are not so close. These are pretty different. So this is one of the downsides to doing a linear approximation. We only shifted away 2 degrees, which might feel like a small movement, but for this function, a lot happens in those 2 degrees. So let's take a look at a graph. Here we see the blue curve, that's our sine of x. That's the function, the true function. And then we've plugged in pi over 3 to find the point, the known point on our function. Then we calculate our tangent line, and we're comparing the actual value, the blue dot, to the approximate value, the red dot. And visually, we can see these are very different from each other. And the reason why that happened is because we traveled too far away from the pi over 3 known value that we started with. This function turned around, but the tangent line doesn't do that. Because it's a straight line, it's not going to turn around like the function did. So when using linear approximation, you have to be very careful that you don't travel too far away. This is the idea of linear approximation, to approximate a function locally. We would not consider this local because too many things happened between the known point and the approximate point that we've come up with.